So as the title of this video might indicate, this is my 500 subscriber special. I started this channel, or at least I started posting regular videos about a year ago. It's beginning of last January, and since then I've been posting videos on a fairly regular basis, and I've been quite pleasantly surprised by the response I've had. The channel's been growing slowly, and I was very surprised a few days ago when I checked and found that I now have over 500 subscribers. And I want to thank everyone that's subscribed to my channel. I want to thank everyone that's left comments. They are much appreciated. I will always try to respond to comments, whether they're positive comments or negative comments. Both are welcome. The only thing I would say is if you feel obliged to leave a thumbs down, then an accompanying comment as to what you didn't like about the video is always useful. And thank you for everyone that has left positive feedback. It's very encouraging, and although my channel's not monetized, the subscriptions and thumbs up are much appreciated. They really do help. So as I said, my channel's been growing quite steadily, and I've got some very interesting projects coming up for this year. With some recent developments, I should be getting access to some even more interesting equipment, which will really help in terms of trying to promote what my channel's all about. And that said, you might be wondering why the camera's pointed at this clock. If you use YouTube much and you subscribe to this sort of channel, then you might well recognize this clock, or at least not this clock, but a very similar clock. Chris over at ClickSpring did some absolutely excellent videos on building one of these clocks. Absolutely first-rate videos. I couldn't possibly match them, so I'm not going to show you how I went about building this in detail. But I wanted to use this as an example of one of the things I mention quite frequently on my videos, and that is the fundamentals of engineering. I'm not going to try and teach you how to make a clock. I'm not going to go over the detail. But what I do want to do is go through the approach I took to building this clock. I built this probably 3 or 4 years before Chris built his, and we actually took very different approaches to building it. I've actually modified this clock quite a bit during the construction of it. It's built from a set of plans, but both Chris and I didn't adhere absolutely to the plans. But this clock is built from nothing more than raw materials, so steel, tool steel, and bits of brass sheet and mild steel sheets, offcuts of brass. Essentially it's made from nothing more than raw materials, and that was the approach that I wanted to take. I wanted to build this from nothing more than just basic materials. Now on top of that, I wanted to go a step further, and I wanted to not only build this from raw materials, but I wanted to make the tooling required to assemble it as well. So not only have I built this clock, but I've also made all the tooling required to manufacture the parts for it. I will show some images of the parts in a little while. I didn't video this process. I built this long before I started making YouTube videos. But as I say, if you want to see the detail as to one way of building this, then go and look at ClickSpring. He's done some very nice videos on this. So I built this clock. I then went on and built a second clock. So I'll just grab that now. And this is the second clock I built. It's far more complex than the first. It has a lot of features that make it far more accurate, but it's far more complex to build. But again, I took exactly the same approach. This is made from just offcuts, raw materials. Even the screws and bolts and washers are all manufactured by myself using basic methods. And this is what I'm getting at really with this video, is that in terms of engineering, although this is not an electronic device, which is the main topic of my channel, the same principles apply, and that you can get bogged down if you're not careful and be almost railroaded into using certain methods. A good example of this, I was reading a forum a few years ago where someone was trying to get a touchscreen working on an Arduino, and this problem went on for probably 3 or 4 months, and this guy was downloading libraries, getting advice that it was the wrong library, it was an incompatible library, this sort of thing. And I'd developed a system several weeks earlier But I wrote the library, including primitives support, for the touchscreen, including touchscreen support, and in total it took me probably no more than 3 hours. And I think the problem is you can easily get bogged down with trying to find a ready-made solution, and that's what this video is about. It's try to avoid getting railroaded into using a single idea. My videos are not trying to present what I say is the right way to do it. It's not even always necessarily a good way to do something, but I'm trying to give different ideas, different approaches to engineering. So if we look at this clock, for example, because it's far easier to explain with something like this than it is with an electronic device, although this applies equally well to electronics. So for example, if we look at the inner workings of the clock, you can see there are a lot of gears, actually called wheels in the clock, but they're gears everywhere else. And the cutters to make a particular wheel, like any other gear, there's a different set of cutters for different pitches, but these are not the same gear profile that you would find in a car gearbox, for example. They are a different tooth profile, which means the cutters are very specific to clockmaking, and because they're specific to clockmaking, of course they're very expensive. The average cost of a cutter, a single cutter, is well over £100, and in a clock like this you'll need probably at least 9 or 10 different cutters, so that's well over £1,000 worth of cutters just for a single clock, and chances are when you make your next clock you'll need a different set of cutters. So firstly, I didn't want to buy the cutters because A, they're expensive, but also, like I said, I wanted to stick to the basics of engineering. So I ended up making my own cutters. So this is what I ended up producing. As I said, it works just as well as a commercially bought one. I can use these for either cutting the brass wheels or the tool steel pinions. But not only did I want to make these, I wanted to make the tools needed to create them. So firstly, what you have to do if you want to make one of these, and I'll go over this briefly just as an example of what I'm talking about when I'm saying fundamental engineering. I mean finding different ways of producing the results that you want, whether it be mechanical or electronic. So the first thing I have to do to produce a new cutter is obviously the calculations. And it's different for every single cutter, so you need to work out what you need. And one of the first tools we need is the tool to create the radius. So these cutters are made from blanks, so it's just a tool steel blank. So tool steel bar, I chop off a portion, tidy it up and bore a centre hole. I then bore a set of accurately positioned holes at a particular distance from the centre of the cutter. They have to be accurate because they're what determine the position of the tooth tips. And then once I've done that, I need to, of course, change the profile to suit the particular gear I'm cutting. Bear in mind this is effectively the profile of the gaps between the teeth, and 2 of the gaps generate the tooth profile. So you probably can't see it that clearly, but of course there's a radius on the shoulder of the cutter. So the next thing you have to do is create a tool to machine that profile. So this is the cutter that's effectively used to cut this tooth profile. And you need a different one of these for each cutter that you're going to make. You then use another tool you have to make, which goes in the lathe. This creates an offset and allows me to create the offset profile required. It's kind of a hexagon shape for the tooth. What you then do is use an end mill to cut out the tooth profile. It's then honed, polished, hardened, tempered, and then sharpened and polished again. You then need an arbor to use one of these, so you make an arbor. You can see this is a different cutter, but made in the same way, and then the arbor is used to ultimately cut the tooth profile. So in other words, this entire clock and the one I showed you before All the parts were made from raw materials. All the tools required to make it were made from raw materials. Even things like the brooches I made from tool steel, stock steel, and ground them to shape or machined them to shape and then polished them. Making the parts like this, again, tools made from tool steel. So as I say, the point here is that I could easily have spent a lot of money and bought tooling to do this, but it would have firstly cost me a lot of money, but also it would have meant that I was really going down the same road that everyone else had done that had built a clock like this. And I really wanted to build a clock that was my own, totally my own from scratch. And I try to do the same thing with electronics, and as you know, I'm winding a transformer for a power supply I'm making at the moment. I'm not suggesting that you all go out and do the same thing. I'm just showing this as examples of you don't need to be constricted by what you can buy off the shelf. You can go out, you can make your own tools, you can make your own test equipment. You don't have to buy ready-made components. Most of the time you can build something from more basic parts to achieve what you want. And there's far more satisfaction, at least for me, in doing that. So if I just bought a kit of parts and bolted all this together, it would look probably the same, but it wouldn't be anywhere near as satisfying when you start it up and it runs for years on end. The first clock I showed you has now been running for nearly 9 years, so it's ticked well over 500 million times, and it's still going strong. A general estimate is it'll run for 100 years, so it should be going long after I'm not. But as I say, it's the satisfaction in doing that. It's well worth sort of sitting back and thinking about alternate approaches when you're talking about engineering, especially if you're designing something. Try to avoid buying something off the shelf if you can design something specifically for your own product. My company develops wireless systems for monitoring critical equipment, and we developed our own RF subsystem. We don't buy off the shelf RF modules, and the system is one of the most successful that you can get hold of, mostly because we took that approach. We don't use Wi-Fi, we don't use Bluetooth, they're not reliable enough for our system, and using the let's do our own thing approach has obviously worked extremely well, and it does work extremely well in most fields of engineering. So I'll just show you some of the parts in these clocks. They are quite nice to look at if you're not familiar with this sort of thing, but just bear in mind that what I'm trying to present here is that it is possible to produce parts that will meet your requirements, even if you make them from scratch yourself. You don't necessarily need to buy an off-the-shelf item to get the thing that you're looking for. And if you think of the design first and then what you need to fulfill that design, you might find it's requiring something you can't buy off the shelf. But that's good design. That's something that you're sort of pushing the boat tight, you're doing your own thing, and that's really what I'm trying to encourage with this channel. So as I say, any feedback is welcome, but what I'll do now is just have a quick look at some of the parts that went into building this, and again, comments, feedback are welcome. So this is just a random selection of the parts, just so anyone that's interested, you can see what went into making the clock. So this first part is the main arbor. This is what the main barrel runs on, and the main barrel holds the main spring that drives the clock, provides power for the clock. That's fed through this, which is the fusee. This compensates for the changing torque that the spring delivers depending on how wound it is. So it evens out the torque as the clock winds down and makes the clock more accurate. And then there are various parts that go into making all that work. You need maintaining gear, maintaining power so the clock keeps running while it's being wound, and this is the ratchet for that maintaining gear. And this is the maintaining barrel and the fusee. This is the assembly that keeps the clock running during winding, and it is also what allows the clock to compensate for the changing torque from the mainspring as the clock winds down. One of the main things you can see here is the roller bearings that I fitted. Normally these would be plain bushes, and this is just a random selection of the parts. Again, you can see the roller bearings that I used, and these were to make the clock more efficient. It's the main thing with the clock is to keep the friction down as low as you can, and this is the sort of ideas I'm talking about with engineering, is making these small changes made the clock more efficient, and it will run longer on a single wind. And the various parts that you need to put together and make. This is one of the pinions. It was designated as a lantern pinion in the design, but I changed it and put a back plate on, support plate. And again, this is the sort of thing you can do. It's you're not necessarily constrained by the original design, and it's nice to experiment and come up with different ways of achieving the same thing. This was cut using one of the cutters I showed earlier. That's assembled onto an arbor and one of the wheels. You can see this is the second arbor, and I fitted a roller bearing to this arbor as well. I fitted roller bearings all the way up to the third arbor. Beyond that it would have benefited from jewels, but I didn't want to go to the time, trouble and expense of using jewels on this clock, so I just used plain arbors from the third arbor upwards. But the roller bearings do make a huge difference to the operation of the clock, and will also in theory make it last a lot longer because they'll cause less wear. This is one of the tools that I needed to make as part of the assembly process. This is a depthing tool, and currently it's got the escape wheel, and it's also got the pallets. These are very tricky things to make, and the depthing tool really made this easier. You can see the original brass prototype that I made. It's making tools like this and the adapters for tools like this that really make a big difference and allow you to experiment a great deal with the design of the clock. This is the same sort of idea I'm talking about with electronics. You can experiment, try different things. Here we have the arbor for the drive that comes from the pendulum. So it's often thought that pendulums drive clocks, but it's actually the reverse. The clock drives the pendulum. These are some of the screws that I made for the clock. Made of tool steel, tempered and then blued. This is the motion work. This is what the hands are connected to, so it provides a drive for the hands and also the reduction for between the minute hand and the hour hand, and it also incorporates a friction drive that allows you to adjust the clock. Obviously if the hands were fixed solidly you wouldn't be able to adjust the clock, but this assembly also allows you to rotate the hands relative to each other. And this is that assembly dismantled. You can see the bottom right is the friction drive system. Then a set of hands. These were cut from 1mm mild steel, and they're polished. Obviously if you just left them as mild steel they would corrode and they don't look particularly nice, so they are then blued, which gives them a protective coating, and it also makes them look a lot better. And then there are various other parts that you can make in any way that you want, and in this case this is the stop for the maintaining gear, and then this is the fusee and maintaining gear assembly dismantled, so you can see the various parts that go into it, and every single one of these parts was made from raw materials, and mostly using tools that I manufactured specifically for making these clocks. You can see they're fairly complicated inside, but they're a lot of fun to make, and the main thing is during making this I did make various modifications to the original plans, and then of course the clocks being assembled. Again, nothing really here to constrain ideas, it's just whatever seemed to be a good way of doing something. I did make a lot of changes to the original drawings, but it's whatever you really want to do, and I strongly advise you do the same thing with any project you work on, whether it's mechanical or electronic. It's don't be constrained just because you feel you have to buy something from a supplier. See if there's an alternate way of doing it, and come up with your own designs. So as I said, hopefully you found that interesting, but any feedback is welcome.